let's dive right in. So just to start off, I should say this is a 60-minute slot, and I do not hope to speak at you for 60 minutes straight. So if you have questions or clarifications, feel free to raise your hand, and I would love to have something of a discussion. I just reserve the right to cut you off at any point. That's my one caveat. All right, let's get into it. So this is work done jointly with my collaborators Gavin Gray and postdoc advisor Sriram Krishnamurthy at Brown. This talk, as you might have guessed, is about Rust, and if you're attending IWACO, you might have heard something about Rust. I mean, Rust is the ownership success story, right? It is the most widely used ownership-based programming model today. And I love ownership. Like, I've been using Rust for about a decade at this point, and I mean, it's really infected how I think about software development and software architecture. But getting people to understand ownership has been a persistently large issue in the Rust community. So for example, when you survey Rust developers and ask them, like, which concepts in the language do you find most difficult? You get a histogram like this. So the x-axis here is different features, and the y-axis is how many people say it's tricky or difficult. And at the very left edge is lifetimes and ownership. That's the hardest thing, followed by macros, trait bounds, async, and lots of other fun, also difficult features that we also have research on, but that's not what we're here to talk about today. And so, you know, part of the reason learning matters, right, is that some people never successfully learn Rust, and they just give up due to the perceived complexity of the whole system. I will talk about this more on Friday if you want to come hear my talk then. But like literally, hundreds of thousands of people will read the Rust book and just never finish it. They will not even bother getting past chapter 3 because they see, you know, scary sigils, they see type checker errors they don't understand, and they just bounce right off. And that's not the future I want to live in. I want to empower as many people as possible to use programming languages based on the ideas coming out of our community, the PL community. That's really like exciting to me. Now, I'm not the first, by the way, to try and make ownership easier to understand. There's actually a really wide litany of diagrams that people have created to illustrate ownership in a variety of ways. But one thing, a really important thing to me is people who create these kinds of diagrams, they have not engaged in any sort of systematic evaluation of these diagrams. There's no real evidence or data saying this is effective for learners, nor are there really theories to generate these diagrams to say we really believe this is solving people's conceptual issues about ownership. And so that was, for me, the motivating question in this project. How do we systematically make ownership types easier to learn? And by systematic, I mean you could just try writing another textbook or creating another diagram. But we wanted to build something grounded in people's actual experiences and not pulled out of thin air. And at a high level, that process looked like 3 steps. First, we needed to understand what misconceptions of ownership that people had. Then we designed a new pedagogy, including a new visualization, to address these misconceptions. And then we compared the pedagogy against a baseline approach of teaching ownership. Now, there's a lot to unpack in these 3 bullets. I'm going to spend more time today than I have in any other talks in the second bullet really emphasizing the visualization, because I think especially to other folks who are interested in ownership, thinking about how you might visualize your own type system or explain it to people is probably really salient. But I do want to cover the full research experience because I think it really matters to get the context of what led to this diagram and what followed it, and not just the actual thing that we made. So let's dive in. To understand misconceptions of ownership, our goal was first to create what's called a concept inventory. Now, what does that mean? So there's a really fun story from the early 1990s where a bunch of physics teachers got together and they said, we feel like our kids just aren't learning the physics that they're supposed to. And so they created a test that they called the Force Concept Inventory, cited down there, it's a cool paper, to test whether their students had one of many possible misconceptions about the concepts of force in Newtonian mechanics. So this is a concrete example of a question in their test. So you have a guy spinning around, and there's a ball attached to a string, and then the ball detaches exactly at this point, and then it goes in one of these 5 directions. All right, I realize this is not a physics workshop, but maybe you can take a guess.
For B or B?
All right, votes for B. So that is the correct answer. Congratulations. You have the correct conception of, in this case, centripetal force. And so this is a fun problem. The reason this question is clever is not just that it tests your understanding that this is correct, but that each of these alternatives, the distractors to this multiple choice question, were very carefully selected by the teachers who made this test to correspond to misconceptions they repeatedly observed in students both before and sometimes even after their physics classes when trying to reason about centripetal force. And this idea has kind of caught on outside of physics. Lots of people have gotten interested in building these kinds of targeted tests. And that was what got us excited too. What would a concept inventory look like for ownership? And building one is useful here for two reasons. First, in the course of building it, we would have to figure out what common misconceptions are. And then second, once we have this test, well, now you have some kind of means of evaluating the efficacy of your work downstream. You can say, oh, if we've done something we think helps people improve their understanding of ownership, they should do better at our ownership test. That's the idea. So to start building this test, we looked for common patterns of Rust code where people report struggling to understand ownership concepts. Where else would one go than Stack Overflow? So we went to Stack Overflow and looked for questions tagged with Rust and specifically sorted by their frequency metric, which is not the same as top voted, and I could get into the details later if you're interested. And when you do this and you filter down for the questions that are related to ownership, you find a lot of questions that look like this. So they'll say, is it possible to return either a borrowed or owned type in Rust? Blah, 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 blah. Concrete code example. This is the kind of thing I'm interested in. I'm not sure how to express this, for instance. And what we would do then is say, all right, this is a great representation of something that people frequently run into when they go off, write Rust in the real world, and then, bam, borrow checker error, or some kind of conceptual confusion. So what we do is take this program and clean it up. So we get rid, for instance, of external imports and other details that aren't super salient, and produce these new snippets of code. So this one, make separator, takes as input some kind of reference to a string and stir. It returns a reference to a string. And then the contents of it are, if this is empty, then I allocate a capital S owned string, and then I try to return a reference to that. Otherwise, I return the thing I got as input. So this is, but this won't compile. This does not pass the borrow checker. And what we were thinking about is once we have situations like this, we want to test somebody's understanding of ownership in this context. And we felt that there were three questions that corresponded to different stages of reasoning about ownership. So first, what error message would you expect to get from the compiler? If the compiler didn't reject this function, what is a program or an input that would violate memory safety, if one exists? And what is an idiomatic fix to this function? So the first question says, understand the type checker itself, like the static semantics. The second question is more oriented towards the dynamic semantics. And I think the second one is particularly interesting because it's not a skill that a Rust developer normally practices. But it very much corresponds to this common idea that learning languages like C is useful to learning Rust because you bring your intuition about segfaults and things to at least motivate, if not understand, the benefits of Rust's memory safety machinery. And then the third question is about teasing apart, OK, can people fix these functions, as well as are their fixes idiomatic? Does it involve anything unnecessary? And the question then is, how does this relate to these other two questions? Does a better conceptual understanding lead to more idiomatic fixes? And so just in this concrete example, valid answers would be things like returned reference does not live long enough. For the input, you would say call this function with an empty string, and then use that dangling pointer. And an idiomatic fix depends on your level of sophistication. So for a novice, I would expect returning an owned heap string, capital S string, is valid, but that would involve reallocating the string on the heap. The more sophisticated answer is to use something called the cow type in Rust, which expresses the concept of something can be either owned or borrowed, but you likely need to have some experience before you would know that kind of thing. So what we did is we collected 8 snippets for a range of ownership problems shown in this list. So these were different categories of ownership errors we saw reported on Stack Overflow, And then we got sort of a canonical snippet that embodied these different concepts. Then we have 3 questions per snippet, so that gave us 24 questions total. That became the basis of the ownership inventory. So, having generated those problems in a somewhat data-driven way, our question is, how well can Rust learners solve these problems? Can we identify misconceptions in the ways that people try to answer them? So we've started by running a small user study where we recruited people who had just, question.
Do you have a way to tell if that list is exhaustive in any way?
Do we know if this list is exhaustive? No. I mean, well, in a technical sense, you could maybe go to the compiler, like the literal borrow checker, and look at the different errors that it emits. But that's a sort of technical definition of error. This is more a situational definition. And this also is almost not exhaustive by definition. There are lots of other errors. I can give you errors that are not on this list. But I think the important thing is this is a prioritized list. Our point is these are the things people are most commonly reporting on Stack Overflow when they run into these issues. Therefore, we believe these are the most important categories for us to test people's understanding. Question?
Short corroboration of your answer. I have run a master's thesis, or supervised a master's thesis, trying to, in particular,
It was on.
Okay. Trying to categorize different kinds of ownership patterns, essentially, and just figuring out the different kinds of things you can do is definitely not straightforward.
Right.
So it's much more difficult than you'd think.
Yeah.
So making an exhaustive list would be very difficult or possibly impossible.
Yeah. Yeah, thanks for that. And I should point out there are other people who have looked at this question more rigorously than we did, of more systematic surveys of lots of Stack Overflow data or GitHub repositories to try and guess at the distribution of ownership errors. We sort of relied on, literally it's just Stack Overflow, Rust, sort by frequent, and then we picked the top 15 we could find that were related to ownership, and then condensed them if we felt that 2 were really talking about the same topic. So part of this is about, we engaged in a process that I think was better than just pulling it out of thin air, but could benefit likely from possibly a significantly more rigorous investigation of that aspect. All right. So just to recap, we came up with these questions. We wanted to run a user study of how well people could understand or answer these questions after they had read an introductory Rust textbook. And specifically, we asked these questions in an open-ended way because we didn't know what the misconceptions were. So we asked, what error do you think it would get? Text box, you tell me, as opposed to here's one of many distractors. We went in and graded everyone's answers by hand. And our main observation was that being able to connect the static to the dynamic semantics was really key to producing idiomatic fixes. What exactly does that mean? So in total, learners could answer the first question about predicting the Rust compiler error pretty effectively about 64% of the time. But participants were much less effective at writing counterexamples, so they only got it right 31% of the time. And when they were asked to justify why their counterexample was a counterexample, only half of those 31% could do that correctly. So this was a very difficult problem for our participants. And the reason why this matters is that a shallow understanding of question 2 seemed to correspond to a limited ability to idiomatically fix code. And here's just one example from the data. So one of the problems involves 2 conflicting borrows. So you say if let sum curve equals self.getCurve, that borrows effectively one field of a struct. And then for score in self.scores, which is a vector, .ittermute, tries to mutably borrow a different field of that struct and then mutate it. And Rust flags these 2 things as conflicting borrows. This is actually a completeness problem and not a soundness problem. This is a safe program, and the problem is convincing the compiler that it's correct. And people who did not recognize that there did not exist a counterexample, that this was a legitimately safe program, were more likely to write answers like this, where you would say for score in self.scores.clone.ittermute, which does get this to pass the borrow checker, but has a completely different semantics, because now you're mutating a copy of the data you immediately throw away. And so that's the sort of problem we were observing. And another way to say that quantitatively is that people who correctly answered the first question right about the compiler error were 1.1 times as likely to get the third question right about fixing the function. But people who got the second question right about getting the counterexample, we're twice as likely to be able to idiomatically fix the code. So the sum of this evidence, that as we interpreted it, is that existing approaches to teaching ownership are certainly enough for people to recognize patterns of bad code, but there's something missing about a conceptual depth as to why the compiler is rejecting their code. And so we started to think, what would a pedagogy look like for addressing those misconceptions, that lack of conceptual depth? And in particular, we conjectured that the key concepts that learners were missing was within the dynamic semantics, the issue of undefined behavior. Like, what kinds of mistakes is Rust trying to prevent you from? And within the static semantics, there was the question of unsoundness versus incompleteness. When is Rust protecting you from genuine undefined behavior versus when is Rust over-approximating in a way that rejects safe code? But the really interesting question still is, how much do we need to teach Rust learners about these concepts in order for them to be productive? So what I mean by that is, like, when we talk about ownership in Rust, there are different levels of abstraction to the conceptual model of ownership that we give to users. So a maximally abstract conceptual model is Rust prevents memory errors. And this is maximally abstract in the sense of it eliminates all details about how ownership works in Rust. Moving slightly down, you could say Rust enforces aliasing XOR mutability, which is a slightly more mechanistic statement, but still you can get more concrete. Like, how does Rust enforce this? It tracks the live range of borrows. Well, what does that precisely mean? I could give you a mathematical description of what it means to track the live range of borrows. But is that math even right? We have to look at the source code of the borrow checker if we want to get the most concrete conceptual model of how the ownership checker works in Rust. Now, a very key observation, we don't want learners to be up here, and we definitely don't need them to be down here, right? It's way too much to ask someone to get a PhD in programming languages before understanding Rust. It's, right now, I think after reading Rust textbooks and tutorials, people tend to be around here. They certainly get the basics and maybe get sort of the principles, but they're mostly just pattern matching on code, and they say, oh, I can't have two mutable borrows or something like that. And we want someone to be a little closer to here, such that they understand the mechanisms enough that they can, say, for instance, understand the distinction between soundness and completeness when that matters to idiomatically fixing their code. And I bring this up because, yes?
How did you determine where learners are today?
This is essentially our impression from the data. So like the test that we ran, we would say the answers that we saw were suggestive of a conceptual model at this level of abstraction. Very few people could answer at this level. Yeah. And I bring this up too just because I think this is a really useful framework for anyone thinking about pedagogy of advanced programming tools. Nobody, like your average user will never get down here, even though many of you on the tools that you work on do exist at this level. And also, people can be in this middle and do amazing things, use your tool to do awesome stuff without ever fully understanding what's going on. And that is a super interesting phenomena to me that I don't think we as a community know how to grapple with, of like, what is this Pareto curve of the most productive I can get you at a given level of information I'm willing to teach you? That's an interesting idea. So we tried to, look at a new point on that Pareto curve. If we try to tell someone just a little bit more about how the borrow checker works, what do we think is the right thing to tell you such that you become better at working with the kinds of errors we saw? And just to make this a little more concrete, so for the dynamic semantics, we wanted to get specific enough that people understand undefined behavior, but we don't need to get into the details of, say, like register allocation, alignment or struct packing, things like that. And so I'll show you the conceptual model of the dynamic semantics that we gave people. And that's embodied in this diagram. And I'll walk through it briefly. So let's say you have a vector. You say let mut v with the elements 1, 2, and 3. Then that is represented by a vector v on the stack pointing to the elements 1, 2, and 3 on the heap. If you then borrow an element of that vector, so you say num equals and v2, then that looks like num on the stack points to 3 on the heap. When you add an element to the vector, then so if you say v.push4, that resizes the heap allocation of the vector in this case. So you now have a new allocation, 1, 2, 3, 4, and the pointer num has been invalidated. So this is null pointing to old memory. And then if you try to use num, so if you say like println star num, then that's undefined behavior, a use after free. And the thing to reflect on is the conceptual model of Rust's dynamic semantics embedded in this diagram. This is not how Rust actually works, right? The reference num might never exist on the stack, but that doesn't matter, right? The point is that's not a relevant detail to understanding ownership. Again, that's kind of obvious, but I just want to emphasize it. I think these are subtle and important decisions about the representations of the language you give to someone. Now, this diagram also looks like something that you might draw by hand in an Intro to Systems class, but it's actually automatically generated, because the Rust compiler has an intermediate representation called the MIR, and the semantics of MIR really actually closely corresponds to the conceptual model of Rust that we want to give people. So Rust has an MIR interpreter that it uses for constant evaluation. We hook into that infrastructure to interpret any Rust program and then extract the state of memory at each step. One other kind of fun fact here is we are interpreting a Rust program that doesn't pass the borrow checker. That might seem a little weird. You can't normally ask Rust to run something that doesn't compile. But that's the cool part. We're interpreting it. We're not compiling it. And so an important thing that this tool does is we can show Rust learners the counterfactual semantics of this is what Rust is protecting you from. It doesn't let you run this because under mere semantics, if we relax the ownership rules, then you would run into this kind of problem. That's a nice benefit we get from this type of tool. All right, so that's how we dealt with the dynamic semantics as we built this visualizer. And then we did the same process for the static semantics. And again, I'll walk you through an example, which is a program similar to the one you just saw, but this one is well typed. So we wanted to convey Rust's static ownership semantics by visualizing the change in the state of the borrow checker after each line. And we communicate that through this metaphor of permissions. So here, when we create this mutable vector v, what happens is the v gets 3 permissions: read, write, and own. That's what those letters are. And so when we do something like, say, let num equals and v2, so we borrow an element of the vector, a couple of things happens. First, v loses some permissions temporarily, because while we hold a reference to that vector, we are not allowed to either write to that vector, like add an element to it, or own that vector, like deallocate it or move it somewhere else. And then we additionally have these permissions on num, the thing that holds the reference, and star num, the data accessed through the reference. And the only thing we can do through the reference is read it. We can't, for instance, write to it because this is an immutable reference. And also, note that some operations require permissions. So there's this little orange dot here. And what that means is in order to create the borrow on v, we need the read permission on the variable v, which we have. And so that dot is filled in. And then on the next line, we say print some stuff, and we read the number. And this is the last time that we use num in the program. So a couple things happen. First, the vector v gets its permissions back. This is a flow-sensitive analysis. And so once the live range of this number has ended, then v is now writable and ownable again. But we can no longer access num or star num. And so finally, we are allowed to, at the bottom, push into this vector, which additionally requires the write permission, because this is a mutable operation. And at the end of this, its lifetime ends, and v loses all its permissions.
How do your users react to the fact that basically these, the second and the third line seems to have different semantics, right? So basically the last use of num has different semantics, but it's not obvious from looking at that line that it's the last use.
Yes, great question. And so hold on to that. I will cover that, but I think it's an important observation on the diagram. Any other questions?
On the last line, there's kind of 2 things in different locations, right? There's the use of v to do push, and then there's the end of the scope.
Yes. So the use of v to do the push has nothing to do with the change in permissions. This only has to do with this. So the idea is sort of what permissions you have available to perform operations depends on the state before this line. Yeah. But your intuition that sometimes you might have multiple things happening on one line is a good one, and we will also get to that. Yeah. Mm-hmm.
I guess I have a question. I mean, to some extent, you can define the permissions however you like. It's also like you're teaching
Yeah.
I wonder, why did you go for, thanks. Why did you go for modeling this as losing ownership? Because the ownership of the vector doesn't change, right? The binding is still B, the memory will still get deallocated when B goes out of scope. So
that's right.
Why should I learn this as a change in ownership?
So the key thing, you're right in that this is not a move. And I think this is one thing when you think about Rust that actually is really important to internalize, is the hard part of Rust is not linearity. It's not really like moves or deallocations. That sometimes is important, but the far more common set of ownership-related confusions that people have are around borrows, about when you create references to things and that temporarily changes these permissions. That is the significantly more pernicious thing that people deal with. We do also separately talk about, like, for instance, when you move this vector v to another variable, that old thing would lose all of its permissions, and the new thing would gain all of its permissions. But those are just two distinct concepts we talk about separately. But they're both modelable within this permissions model. I think the key thing is people don't really recognize how, like, when I create this borrow, what exactly is that doing to the thing that I'm borrowing?
I think I understand that. For example, if it were a mutable borrow, it would look exactly the same in terms of these permissions. And I guess I'm wondering, would you not like to keep the notion of ownership separate to distinguish the two cases?
Yeah, no, it's a good point, which is if you have a mutable borrow, you perceive that thing as losing all of its permissions, which is true, and then you regain them at the end. And yeah, so I think there's the fact that that variable is still live and owned during that entire duration, there's no visual encoding of that in this diagram. So I agree that that is like an aspect of the conceptual model that is important, but I think just in our experience and in the kinds of problems we were trying to target and what we saw in the ownership inventory, that was not our principal focus. Yeah. All right.
Alex, could it be also like I mean, this is somehow the interpretation, right? You could think of basically slashing the O not as losing ownership, but losing the right to exercise ownership, going back to Mark's keynote this morning, right? And then you didn't lose it, you just lost the ability to act on it while the borrow is active.
Yeah. All right, sorry, I'm going to cut discussion for a second, and I want to continue talking about this diagram. So what I want to do is, this was a great example, and I want to dig in a little bit to the thought process behind the design decisions in this diagram. So the two main components of this diagram are what we called permission boundaries, these things that tell you what's expected, and the permission steps that tell you the change in permissions between different lines. And I think the biggest difference between our diagram and the litany of related work is that the predominant focus of other kinds of diagrams is usually lifetimes, that the sort of central visual object is lines that show you when variables are used or live, or these rectangles and things like that, augmented with other information, like these locks or these dotted lines or other things that tell you what operations you can do. But we sort of inverted that. Like, I think our belief in the design of this diagram was that the most important thing to understand about Rust's ownership model is, first of all, like squinting at your code and sort of understanding how the borrow checker lumps all operations or abstracts them into these very coarse categories of like read, write, or own. And then understanding how creating borrows and propagating them affects those permissions as you go through the program. We felt that that was more important for teaching learners, and so that was the sort of central focus of the diagram that we created. Additionally, like one thing that I think is interesting about liveness is that liveness is not necessarily linear. So we played around with several concepts early on. For instance, like if you wanted to see the live range of a borrow, if you do something trivial like put a bracket where that borrow starts and put a bracket where that borrow ends, you can end up in these weird situations with structured control flow where this borrow does not actually live here. It's live in a disjoint range of lines. And I haven't seen lifetime visualizations that really grapple with this fact. So I think there's sort of deeper questions here about how to deal with these more complex situations that I'm not even sure what exactly the right thing is to do, but is an open question for these kinds of ownership visualizations. All right, and now I want to tell you more about how we arrived at some of the very specific low-level designs in this diagram. So this is some fun history. So we did a lot of iterating at the whiteboard. By we, just to be clear, my collaborator Gavin did most of the visual design work, and I was the good advisor just throwing feedback into the Discord. And my original proposition to Gavin was I wanted to design something that I called ownership vision. Like if you think about a sort of thermal camera, you have this temperature-oriented view of the world that abstracts out everything except just like the temperature at each point in your field of view. And what I wanted was an ownership camera that would show you a program the same way the borrow checker sees it. So the inspiration here was that like you could sort of abstract out the concrete names and types of these variables and just see them as like, there's the blue square, and it's blue because it's immutable, and the red triangle, and it's red because it's owned, or stuff like that. And this was all very high level, but eventually we got from here down to these little dots, and it was a bit of a ride. And just to speak more precisely about what that looked like, we initially conceptualized this problem as like, one way to think about parts of ownership is you have this subtyping lattice, where if I have a mutable owned type T, I can either use that as an immutable owned type T or a mutable reference to a T. And then either of these types I can use as an immutable reference to a T. And we wanted a way to visualize these types such that it was perceptually obvious whether a subtyping constraint holds or does not hold in a program. So if you phrase this as like a sort of visualization research problem, we're finding a mapping from ownership types to visual marks. This was our first attempt. So we said if you encode ownership as hatching and mutability as color, you have these glyphs. So like the type mut T is a hatched red box, and then an and mut T is just a red box, and so on. So that encodes a specific, or abstracts a specific type along ownership lines. And then in order to visualize a subtyping constraint, we nested these two things together. So the inner box was the actual type. The inner box was the expected type, and the outer box was the actual type. And that way you could like embed this glyph at any point where a subtyping constraint was introduced, and it would tell you the sort of ownership structure of that subtyping constraint via these composite glyphs. And these are grouped. So these constraints on the left are ones that are valid subtypes, and these ones on the right are invalid subtypes. But we felt this was not a good visual encoding, because if I just showed you a random one of these glyphs, you wouldn't be able to just at a glance tell me which of these two categories does it fall into. And that was a priority for this visualization design. So as a second attempt, we tried separating out ownership and mutability into separate glyphs. So here, ownership is represented by whether the square is filled in, and mutability by whether the circle is filled in. And then once you put that into a subtype context, we then have these kinds of like filled in. You have the ringed circle and the ring square and the ring circle, and these are the accepted subtypes. Those are the rejected subtypes. And this was kind of nice because it corresponded to a simple heuristic, where if you look at these and say, all right, if a shape is hollow, then there's an ownership error. That's a very easy heuristic. You can then look at any program that has this ownership information visualized, and it quickly tells you, oh, OK, I get why there's an error here, because there's this I'm expecting something, and I can't actually provide that. And that's visually encoded this way. This is very similar to like if you're designing a data visualization and you're mapping data into like pie slices or bars, then the different kinds of visual encodings you choose will make certain inferences easier or harder. Like, is one number bigger than another? Is a lot easier for two aligned bars and a lot harder for two pie slices. And that was the kind of intuition we were exploring in the design of this diagram. So we were happy with this. We tried running with it. So we started by putting the squares and circles into an editor. But I mean, why does square mean ownership? That's kind of arbitrary. So we tried doing icons like this little hand that I think was supposed to be holding water, and then it became blood. And we thought that was a little macabre. So we decided, all right, let's just go with letters. And so that's how we ended up with read, write, and originally drop, which later got generalized to own. But expanding it out that way is a lot of horizontal space, so we decided to compact that into these little stacks. But even just having these letters scattered around your code was kind of noisy. So the final interface we ended on looked like this. So by default, you see these circles, and interactively, if you want to remember what the letters are, you can mouse over it, and it morphs back into the letters that correspond to it. As well as the colors are visualizing, like orange is the only color we use in the interface for read, and so you know that this circle corresponds to that once you learn that mapping. Anyways, fun little history. That's the design journey that led us to these innocuous circles. And I wanted to show you all this just to emphasize it really was not pulled out of thin air. I do think one can be more systematic than not in trying to explore this design space and think a little bit carefully about how are you representing, say, type level information in different visual ways. All right, so once we had these boundaries, then we started designing the permission steps, these little tables. And the main subtlety I'll just point out here is that these tables are not showing the state of the borrow checker. They're showing the difference in state of the borrow checker. And that requires a little subtlety in the visualization. So you need to talk about 4 different cases. Like if I had a permission before and that didn't change, we visualize that with just a plain letter. If you didn't have a permission and that also didn't change, then we visualize that with this little dash, which is meant to evoke like Linux command line tools. You know, if you see the Linux permissions, they look like that. And then if you gained a permission, we visualize that with the little plus. And then if you lose a permission, we put the cross through the letter. So that way we can talk about this sort of rich space. And even this was subject to some iteration. Originally, we only showed the permissions that changed. So for instance, like this used to be v minus w minus 0, and you wouldn't see this r letter. But we found that learners thought that was really confusing. They didn't understand that v still had the read permission, because that information was tacit in the fact that it was gained up here, and then it wasn't mentioned for the rest of the code. So we felt it was better to be explicit and talk about the state of each permission even when it was unchanged. And the importance of these permission steps is that they emphasize that borrow checking is fundamentally a flow-sensitive analysis, unlike traditional subtyping. Just for example, if I invert the push and the print from the previous example, this is now a compiler error, even though this is still technically a subtype according to the rules that I described earlier, right? This is where the lifetimes of the references also affect the validity of whether or not you have the relevant permissions to do something like push into this vector while a reference to it is live. And just another way to see this model to someone, there was a point earlier about like, we could have invented anything. How like precise is this model, or is this just like a sort of loose metaphor that we put in? There actually is a formal grounding to all this. The way that we think about it is like permissions are under the hood rephrasing the way that the borrow checker thinks about errors. So if you go in and look at how the borrow checker works, and there's actually going to be a talk later today on Polonius, which is the same tool that we used. So that will be exciting. You should go check that out, and it will probably be a deep dive into some of these concepts. But inside of Polonius, one model of Rust's borrow checker, they'll say things like a control flow graph G has some kind of access error under certain conditions. So one way to derive that judgment would be like, if there's a loan on some place P prime live at an instruction I, and that loan is invalidated at that same instruction, that's an access error. And a loan is invalidated if there's a conflicting place P written at that same instruction. And what we wanted to do is rewrite this judgment in terms of permissions. So basically, we wanted to say there's a permission error if some place needs a write permission, but it's missing that write permission. And these are basically the same. We just shuffle around the judgments and end up with a slightly different formalism. So it's not very hard to show the equivalence of these models. I think the more salient point that we're trying to say is just we think that this logical way of representing the like trail of thought, essentially, of the borrow checker lends itself to a better visualization, a more effective conceptual model for learners. That's why we represented it this way. And it's also nice because this is fully mechanized. That's how we automatically generate the diagrams, is by taking the borrow checker's information, turning it around, and then spitting out these permissions. All right. So those are a few perspectives on the visual and logical structure of the permissions model. But this model is not perfect, as several people started to hint at. And I want to touch on a few things that we found in practice that people thought were confusing, that we've either changed or are just open problems. So one big change was how our own permission interacts with copy types. And to understand that, I'll show you a concrete example. So here you have a vector v that contains strings. You create a reference, sref, to an element of that vector. And that sref only has the read permission. So then if you try to do an operation like let s equals star sref, you dereference that. This is rejected by the compiler. And similarly, it's rejected by the permissions model. Because if you let this happen, then both s and v would think that they own the same string. And then you would end up with a double free or a use after free or something. But this behavior confusingly changes depending on the type of data inside the vector. So if I replace those strings with numbers, so I have a vector v and the same program otherwise, nref points to v0, let n equal star nref, this program compiles. All right, now you need some way of explaining this behavior. And originally what we did is we said that we adopted the rule that a dereference always requires the own permission. And so the only way to make this compile is to say then through that reference, or the data accessed through the reference, also has the own permission. And that's kind of confusing. Like, a lot of learners pointed out that they felt this was inconsistent with the conceptual model we were trying to build. This claims that, like a foundational statement in the textbook I'll show you later is that references are non-owning pointers. References don't give you ownership over the data they point to. And then we go, oh, but except in this case, you know, and that's not a fun edge case for people to internalize. It's not a clean mental model. And so what we ended up doing was saying, all right, we can just conceptualize it differently. Instead, we will think about these references. And by these, the general category I'm talking about are types that implement in Rust the copy trait, meaning loosely, they don't own any heap data. So it is safe to bit copy them, and no ownership violations will occur. So we say for copy types, they still have the same reference semantics in the sense that when I create a reference, it gets the same permissions as non-copy types. But then we change the dereference semantics. So now instead of RO or RO here, it just expects the read permission. And that's the sort of discontinuity. There's now a different behavior at this point rather than this point. And just from talking to learners and reading their GitHub issues, we think that this seems sort of more conceptually consistent, even though you really could present it either way. So that was one change. Another problem, and this gets to what Cyrus was saying, we haven't really talked about, or people very frequently get confused about whether permissions are prescriptive or descriptive. So what I mean by this is, returning to our original example, a learner might look at this program and they will ask, all right, what edits can I make to this program that are going to be well typed based on those permissions? So I might say something like, can I add star num plus equals 1 here? And the answer is no, you can't. This is a read-only reference. It will never have the right permission, and so you can never put this here. But if I say, can I read num again, let x equal star num? I mean, you told me it didn't have the read permissions, right? But you can do this, because this is sort of prescriptive, loosely, whereas this statement that num loses its permissions here is talking about the lifetime of this variable, which you can extend. You just can't extend past here, right? We haven't really come up, this is just a confusion we walk people through and they get it eventually, but I do think there's probably a better way to convey this information. This is just one open challenge of struggles we've encountered out in the wild explaining these kinds of things. And then briefly, I'll just mention two other problems for the sake of time. One is that sometimes two things happen at once. So like here, if we have a string that is both borrowed but also not used anymore, then you see the thing losing all of its permissions, but that's just because it's not used anymore. It's not because you borrowed it that way. And so sometimes multiple events get combined together, which the static analysis isn't aware of. It just says, oh, it's not used anymore, so loses all its permissions. And this produces an inconsistent conceptual model for learners. They go, oh, well, this is clearly borrow's doing more than I thought. And the other thing I'll mention is we only really deal with one category of ownership errors. There's a whole separate category which has to do with lifetime parameters. Like when you take references as input and you return references as output, when are you allowed to return a particular reference as output? And so like in this case, we're allowed to return this input strings as an output reference. But if we have multiple input references and we don't specify which ones the output type is allowed to alias, then we get an error from the borrow checker saying that's not valid. We've started to try and construct a sort of approximate mental model of this through this flow permission. But long story short, I don't think this works. This is kind of a bad idea, and it's conceptually inconsistent with the sort of flow-sensitive nature of how permissions work elsewhere. So this is also an open problem of what's the best way to visualize and explain this category of errors. All right, so that was the end of my deep dive. Again, I'm sure many of you have questions, but I do want to make sure I get just to finish out on the evaluation piece before I open the floor up. So let me take a drink of water. Refill my enthusiasm, and let's keep going. A diagram is not enough to teach people ownership, of course. What am I just going to throw a diagram at them and they go, ah, that's it? No, you need a pedagogy, right? So what we did is we embedded these diagrams in a popular Rust textbook called The Rust Programming Language. And it looks kind of like this. So we have text explaining it, and then the diagrams get embedded in situ. These are not actually they're not interactive in the sense of you can edit it and get a new diagram. We have a separate REPL you can do that, but this is intended as kind of static content. It's at rust-book.cs.brown.edu if you want to check it out after the talk. So our curriculum basically looks like this. We have 3 main sections. We talk about what is ownership, and this is almost entirely about the dynamic semantics. So the stack and the heap model, how moving things around causes, invalidates your previous memory, and about the distinction between copies and moves. Then we have the references and borrowing, which talks about mostly the examples I walked through today. You create immutable and mutable references, and those change permissions on various paths. And then we have several case studies, emphasizing in particular, I'll just draw your attention, distinguishing between is your program unsafe or is it safe? Because depending on which one it is, you will take different actions to try and fix your program, if you are in the incompleteness zone or in the unsoundness zone. I think that's a really important distinction for helping Rust learners get how to work with ownership in Rust. So we have this curriculum in place. We put it up online in this Rust book. We felt that it was a better way to teach people, but was it? We had to find out. So the last step was to compare this pedagogy against the baseline, the original Rust ownership chapter. We needed people to test this. This is a tool for people to learn, so we needed some people to go through our book. Rather than pay a large number of undergraduates, we went a slightly different route. We had the people in the authors of the main Rust book put an advertisement to our book in their book. Awesome. Shout out to them. We really appreciate it. We've had 100,000 people come and read our book in the 2+ years since. So everybody wants to learn Rust. Free participants. It's a win-win for everyone. Then we wanted to ask, how do we evaluate these readers' understanding of ownership? This is where we truly close the loop. We bring back the ownership inventory. So we took all those 24 questions I mentioned earlier, and now we made them multiple choice. We didn't just invent these distractors either. Remember, this is a concept inventory. So the distractors were taken from the most common incorrect answers given from people in the original user study. That's how we seeded this. So we made all these multiple choice questions. We stuck them in different parts of the Rust book. Then we ran basically an A/B test. So we put the test itself out into the baseline version of the book. So people are learning ownership as normal. They take this test. We get the data. We put in our new curriculum. People then read our new curriculum, different people. Then they take the ownership inventory. We get data back. We use cookies to figure out who is who. And then after about, I think it was like 6 weeks per condition, we ended up with about 150 people in both conditions who completed enough of the inventory that we could compare their scores across most of the test, except the ones that were very at the end of the book that not many people answered. The main result is that compared to the baseline TRPL pedagogy, the permission pedagogy improved scores on average by 9 percentage points. Yeah, that's a letter grade from F minus to F. There's clearly a lot of room for improvement. These are difficult questions. But like as educational interventions go, like a normalized effect size of 0.56, I was happy about that. This is progress, measurable progress, even if it's not perfect. Just drilling in a little bit, the main thing we found is that most of the improvements were on the picking counterexamples question and the fixing the code question, and not on identifying the compiler errors. And honestly, we thought that was reasonable because the pedagogy we were going for was oriented specifically around helping people with these questions. So we thought that was a good reflection that what we expected to happen was happening. All right, now there's still lots of questions, like transfer. If people do well on the questions we came up with, can they debug ownership questions out in the wild? Are we really helping people once they go off and do Rust in the real world? Not sure. We hope so, and we think that by grounding this data in Stack Overflow and our user studies, we have more confidence that's true. But I think that's a great example of a second step or another step that we hope to look at is tracking people longitudinally to understand the efficacy of different educational interventions on their long-term Rust trajectories. So just to make sure we have time for questions. 3-step process, understand those misconceptions, design that pedagogy. You now understand how much sweat is packed into this one sentence, and then compare that pedagogy against a baseline with every Rust learner you can find. It's the rough summary of how we try to make Rust's ownership model easier to learn by explaining it and visualizing it in a new way. Thanks for listening.
Thank you for a good talk. As a person who works in visualizations and trying to help students understand, the one thing I noticed that wouldn't it help if you had like an informative message that went from one of your visualizations to the next, explaining what would happen? Wouldn't that be? Have you have any thoughts? Have you thought about that along those lines?
When you say explaining what would happen, like what?
Why does the ownership change?
Oh, yeah, great question. So let me pop this over. So this is our live demo running. Bump that up a little bit. So the way this works is, in order to explain the reason that different ownership changes or permission changes happen, we have these icons, which we explain more in the book. You can also hover your mouse over it, and it'll say like, path, it's really tiny, you can't read it. It says path is borrowed here. We want more specific messages eventually that are templated, but these are the little icons we use to indicate the cause of a change in permissions. So that's how we help people get a more causal understanding. Yeah, but this still has the issue of if there are overlapping events, we right now arbitrarily pick one, but we should be trying to explain both of them at the same time. That's one issue I mentioned earlier.
Did you collect some data about the expertise of the people that read the book? I'm curious how much you're helping them like learn Rust versus just programming. Because a lot of these concepts are, I think, appear in other programming languages as well, like ownership and stuff.
Yeah. So to the first question, do we collect demographic information? Not directly on most participants. We do have a sign-up form by which people can volunteer for more experiments. And of the people who sign up for that form, for which we collected a little bit of additional data, I think the most salient thing is that most people reading the Rust book do not have systems programming experience. So part of what this pedagogy is, especially I didn't talk as much about the dynamic visualizations, but those are really important for people who don't know what the stack and the heap is and need at least some conceptual model of pointers. That is a big chunk of it for that category of people. But even for folks who, there's still like 40% of learners know some amount of C and C++, and I think the explaining ownership is really oriented towards them as well. Some of this is probably general. Again, I think ownership is a general concept, and you can write in an ownership style way outside of languages with ownership mechanisms. But some of it is also kind of specific to Rust. Like, for instance, one of the things we try and explain in the book is incompleteness, especially around field sensitivity. Like, what are cases where Rust understands when you're borrowing a specific field of a struct versus it says, well, you could be borrowing any field of a struct. That's a really common issue people run into, and people don't understand that it's an incompleteness issue and not a soundness issue. And that's a thing we focus on in the pedagogy I would expect is very specific to Rust, or at least ownership analysis.
Yeah. Out of curiosity, did you try just printing each of the events? I mean, instead of just arbitrarily picking one symbol and then the final state, could you just do all?
Yeah. I mean, that's the next thing we're going to do is just like try to list them all out. I think the challenge, like really the other challenge is like, can you drive these back to the source code that corresponds to them?
But not even list out all of the symbols, but just have multiple rows, right? You could have V on 2 rows and then say, oh, first this happens, and then it's not live anymore. Everything goes away.
Yeah, so you definitely could do that. I think that's more of a like, the way the static and like the transfer function and the data flow analysis doesn't draw that distinction. Like you just have one mirror instruction, you pop over that, and you have a change in permissions, and it's not distinguished, like, and that encapsulates a bunch of stuff. And so you would need to enrich the domain you're analyzing in order to capture that like richer provenance, I think. So that part would be a little bit harder, but it's not impossible. I could imagine a visualization that works that way.
Thank you for the great presentation. The borrow checker of Rust has some features that cannot fit into a straightforward mental model like two-phase borrowing. For example, v.push, v.len is actually valid in Rust, but it is sometimes hard to explain. Do you have some idea on how to help people better understand why these codes are valid?
Yeah, so I think two-phase borrowing is a good example. Part of the challenge is, well, I think our model is useful for right now the sort of simpler constructs. And we're almost like downstream of things like two-phase borrowing, because what we do is we basically say, if we go back to the formal model a little bit. Yeah, up here. Up here, what we're doing is basically just saying we take roughly we take these very high-level facts as input. Like someone has already told us when when this thing is live or when these things are invalidated, and then only right before you're about to generate an error, we then swizzle these things around. And that's significantly later in the pipeline than stuff like two-phase borrowing. So I think if we wanted to extend this to explain those sorts of phenomena, you would need sort of a richer model of how these facts are sourced. And that would just be a different conceptual model, or a conceptual model targeting like a different level of the analysis pipeline, which I do think is an interesting question, but would probably need a different technique than what's being shown here.
Okay, thank you.
Yeah.
So maybe one thing that I actually find really interesting about your work is that there's like this, in general, I don't remember or I got this idea from, but there is a distinction between something like language of teaching and language of explanation. What you are developing is a language of explanation that doesn't really need to explain everything that can happen, but it's like a higher level mental model.